So thanks for coming back for the second session. I'm Swan. I was the chair of the computer science committee until middle of November. So we have our new chair also will be appearing later on in the afternoon chairing a session. So thanks everyone for coming again and on behalf of the committee. Right, so the second talk is will be given by Anna Cavalcanti. So she's a professor at the Department of Computer Science in University of York, and also she's Royal Academy of Engineering Chair in Emerging Technologies, a prestigious award there. So her theme, the theme of her research interest is quite broad, but including software engineering for robotics and formal verification, theorem proving, model checking, testing. And today the talk is basically combining these two into talking about in terms of verification of control software, right, for the RoboStar and your lab, basically. Yeah, thanks.
Thank you very much for a kind introduction. Thank you very much for the invitation to be here. Like Rod, I'm absolutely delighted to be able to be here in person, talking to people in person. But also good afternoon to those that are online. It's a new world and that's now extended, so that's very positive. So yeah, I'm the director of the RoboStar Center for Software Engineering for Robotics. And when I say software engineering, I absolutely mean that if you are developing software, you are being backed up by techniques that are founded in mathematics. If you're not doing that, it's not engineering, it's hacking. Right? That's the position that we take in RoboStar. So RoboStar is a very extensive framework to deal with several aspects of the design and verification of a robotic system. And today I'm going to tell you more about the work that we've been doing more recently on verification of neural networks that are being used for control. So I'm going today to tell you more about the motivation for our work, the RoboStar framework and how to address the issues that I will raise. In particular, I will tell you about Robotics, which is one of our core domain-specific modeling notations, and then how we extended it to deal with applications that involve neural networks. With this new language, with this extended version of RoboChart, I'll tell you about the semantics that we have provided for this language, the mathematical semantics, and the verification by proof technique that we are pursuing, and concluded some future work. So motivation. It was interesting to see some commonalities between the issues that Rod has raised, working in an entirely different area, with the issues that we perceive in the development of software for robotics. So the issue is that robots are getting out of their cages. Rod talked about the warehouse, the Amazon warehouse, and how automated it is with robots and so on. But even that environment is structured in some ways. You have an understanding of where the shelves are. The operators that are dealing with these robots, they are employees that are trained. Robots are really getting out of their cages. We are now dealing with robots that might be able to help people with disabilities to get dressed. That's in a completely unstructured environment, when robots used to be only in factories, in fully structured environments. But we need to trust, again, a commonality of the areas. We need to trust these robots if we are going to allow them to come to be among us. And the current approach to software engineering, in quotes, is completely ad hoc. It's code-centric. Again, a common problem is that what we have in many cases are not software engineers, but they are the control engineers, the roboticists, the mechanical engineers that are looking at the problem and say, there is quite a lot of interesting control engineering going on, but the programming, it's just a bit of programming, I don't need to worry about it. And then we have this ad hoc approach where the first thing that they do is to start writing code and testing and trying them to the best of their ability. On the end, all they can say is that they haven't found any mistakes. We in RoboStar, we are pursuing the development of a collection of domain-specific modeling languages with tractable mathematical models that will allow us to verify the systems and have a much more engineering-based approach in the appropriate way. The challenge that we have in this area is the integration of the reasoning techniques, the modeling language and the associated reasoning techniques, because we have artifacts of a various different nature involved in a robotic application. It's a systems engineering problem where you have to deal with the software, with the hardware of the robot and its embedded software, and with the environment, the robot, of course, being able to sense the environment to affect that environment. So there are heterogeneous models, and we need to deal with that problem. So one of these many aspects is the issue of learning, of intelligence in these robots, and that the use of neural networks is very common. We in particular are interested in neural networks that are being used for control of the robot, and there are several tools that have been developed for verification of these neural networks, but they focus on the neural network. They are described and can be used using the language of the neural network, the inputs as hyperdimension shapes and so on. But for us, we don't want to have to deal with the problem at that level. It's a systems engineering problem. Colleagues in the industry have told us we want the properties to be described, we want the language of the verification that we're going to be carrying out at the level of the system. So that is the challenge that we face for neural networks for control. So the RoboStar vision is that instead of a code-centric approach to development, we use a model-based approach, a model-centric approach to development. And when the models are very comprehensive, they can cater for software components, for the software as a whole, for the physical robot, for the scenarios, not the full environment, but scenarios that are used in simulations, for example, operational conditions, the assumptions that you can make about your environment, human behavior, you can not describe the behavior of full behavior of a human, but you can make assumptions about those human behaviors and particular properties. So a very rich variety of concerns and aspects, and they need to be integrated, and the way that we integrate them is with the use of a mathematical modeling framework that is called the Unifying Theories of Programming, or the UTP for short. That is a predicative account of a relational model that can be used to capture several paradigms of modeling and programming, and that we employ to obtain this rich integration of models and techniques. And of course, when you put your effort into writing these models, you want to derive value from them. We want to derive value by generating simulations automatically. Simulation, a very widely used technique for analysis and design in robotics. We want them to be generated automatically as well as the code. Automatic generation of tests also becomes possible, tests both to exercise the simulation, but also to apply to the system, and proof using model checking, proof using theorem proving. In the particular case of learning that we're going to be discussing today, we are focusing on theorem proving due to the very large state space that we have to deal. All these to provide integrated, consistent evidence of properties of interest. Safety is a main concern for us in York, but there are some of us working in security, some of us working on more general concerns about ethical properties, legal properties, and so on. They all apply when the robots are being used among us. We have a significant asset, which is a tool called RoboTool that allows us to use these notations and to apply the techniques as well. It's application agnostic, but we have been working on quite a few applications that I would like to mention here to you. One of them is the robot-assisted dressing that I just mentioned. RoboStar is part of the UKRI Trustworthy Autonomous Systems program. We have a presence in the verifiability node and in the resilience node, and the robot-assisted dressing is a particular collaboration with colleagues from Bristol, Sheffield, and Nottingham in the context of both nodes, actually. Verifiability dealing with the issue of modeling of the robot, and the resilience node dealing with issues of social, legal, ethical, empathetic, and cultural issues and properties of this robot. Another example that is being dealt with in the context of the verifiability nodes, the firefighting UAV. That's colleagues from Leeds, Manchester, and King's College. We are concerned in York with the development of automatic generation of tests. Others are interested in runtime monitoring and testing at the system level. But we can still deal, our focus is not industrial robots, but we can still deal with industrial robots. In particular, RoboStar Norway have put forward a case study of an industrial painting robot that has a critical safety property, because this painting can discharge sparks that can cause ignition and cause harm both to property and to humans. So they have used RoboStar technology in collaboration with technology from other developers. Simulink, in particular, if you heard of it, very much a widely used tool. And the modular approach that we adopt in RoboStar is particularly suitable for combination of a variety of techniques. We have a few years ago dealt with a small vehicle that's been developed by colleagues in the UK, Connected Place Catapult. That's when we dealt for the first time with the very widely used middleware for robotics that's called ROS. We have worked with a chemical detector as well. That's the colleague of the work of our colleagues in York that are interested in biologically inspired algorithms, and developed these little robots to go and find and flag the presence of dangerous chemicals via robotic nose. In the interest of energy saving, we have contributed as well with verification of a vacuum cleaner to reduce the costs of solar panels by automating the dusting that is necessary to keep them efficiently. So a very wide range of case studies, and if you'd be interested, you can go to our homepage and you find more. But what have we been doing? I'll give you a short overview of the RoboStar framework. The connotation, which is the platform for the work that I'm going to describe today, is RoboChart. It's based on state charts being, or state machines being commonly used by the robotics community, not necessarily as models, but certainly as drawings. I draw a very clear distinction between a drawing of a machine, of what looks like a machine, and an actual model. An actual model needs to have a syntax, needs to have a semantics, needs to be able to be handled by tools. If you basically use Microsoft Visual or any other drawing package to draw a picture to put in a paper, that's not modeling. But they're very close to using state charts, and so our notation is based on something that is palatable to them. We have a simple component model that allows us to define the parallel execution of these state charts, either communicating either synchronously or asynchronously, but crucially platform independent, so that the capabilities of sensors and actuators that are necessary for the software, they are captured by events and operations in a model. And crucially also a timed language that's distinctive of RoboChart when you compare it to many other options. It's a language that allows you to define budgets and deadlines for operations. It's very difficult to find a robotic application that's not timed. And from RoboChart, you can, I don't expect at all, like I didn't expect you to read the example that I had here on the right. I also don't expect you to read this here on this diagram here on the right, but what it's trying to do is to illustrate RoboChart here at the top left-hand corner of a collection of other notations and techniques. And these other notations and techniques allow us to derive value, as I described here on the left. From a RoboChart model, we can get a simulation model which is a cyclic mechanism. It's the difference between a design model as a reactive behavior definition. You have in a simulation, you have a cyclic mechanism from which you can develop simulation code, all that automatically, no need to redo a model. Automatic test generation, I already mentioned. You can associate it with RoboWorld, which is a controlled natural language to specify operational requirements. From RoboChart, you can also derive scripts that allow you to use model checking using FDR. And for the version of RoboChart that includes probabilistic choices, the work of my colleague Jim Woodcock, who's here as well, we can derive scripts for use of the model checker Prism. Theorem proving to deal with the issue of state explosion that is carried out in our work using Isabelle UTP. It's an encoding in Isabelle of the defined theories of programming that I mentioned. And we also have a language for specification of property called RoboStar. A lot of ongoing work on deriving value as well to deal with human behavior, to deal with safety cases. But today I'm going to concentrate on neural networks. So, neural networks in RoboChart. The work that it's very challenging to bring the reasoning about the behavior of a neural network in the context of the system. We want to be able to verify not properties of the neural network, but properties of the system, which happens to include a component that is a neural network. So at the moment, we deal with trained neural networks, a particular structure, they are feed-forward, fully connected, and have a ReLU kind of activation function. That's what we're dealing with at the moment, at least in experiments. So what's the approach? The approach is that you use Robo2 to develop a RoboChart module that is the description of a control software. And then you're going to identify inside that RoboChart module a component that is a controller and operation that's cyclic and memoryless. If it's not cyclic or memoryless, you cannot implement it using a neural network. So we want to identify that component. If it's not there, you can use the traditional notion of refinement or time-wise refinement in particular to restructure your example to get such a component. When you have such a component, then you have the option to change it from a traditional controller to a neural network. And with that, we open the possibility for automatic generation of Java code using a library called JCSP, which allows you to capture the paradigm of communication that we adopt in a process algebra called CSP, and I'll tell you a bit more about it in a minute. That's not the work that we're not suggesting that people implement their robotics applications or even their neural network using JCSP. We have used that work to validate the semantic models that we have created, and have used some assertional reasoning with JML to prove properties of it. Something else that we are pursuing and we will propose as a way of proceeding with the design and the verification is to provide the C and C++ simulation for use with the robotic simulators, traditional robotic simulators like Copilot or Gazebo and so on. Right, so we already have the facility to simulate, to generate code for a simulation without the neural networks, and now we can we pursuing the possibility of doing that in the presence of neural networks. It's not that complicated. The more interesting part comes here. We use a process algebra to give semantics at the timed process algebra to give semantics to RoboChart. And that is automatically generated, that semantics is automatically generated by Robo2 to provide a way in which the roboticists can can benefit from the work that we do without needing to deal with the formal methods behind the scenes. So our approach very much in line with Rod was saying that we got there when people are using formal methods and they don't even know about that, it's hidden. That's what we are pursuing here, the generation of that semantics automatically. But we can also generate the semantics of the ANN automatically, and then we can translate this process algebra CSP can be seen as a front end for this richer semantics described in the UTP, in the unifying theories of programming. So we can translate or we can encode actually the CSP semantics using the UTP, so this predicative relational model. And then we have a notion of conformance. The notion of conformance that we need to use needs to account for loss of precision that we have that when you're dealing with a neural network, dealing with the real numbers. So the standard notion of refinement will require no loss of precision at all. We need to be to understand that that's not going to be possible. We want to show that there is a notion of conformance, there is a conformance in behavior, but that there may be some loss of precision that we want to tame. We want to say it is no more than an epsilon that's given as a parameter for that notion of conformance. And then we can use a combination of Isabelle UTP and Marabou. And in fact, you could do everything in Isabelle UTP, but for practical reasons, you would want to use the tools that are tailored, the SMT solvers or SMT-based tools that are tailored for neural networks. And so that is the approach that we are pursuing. So here's a little example. A very little example of a segue. It's not a segue that we have developed. We bought it out of the box and we developed a model in RoboChart for the code, for the C++ code that came with it. So here I will explain to you what's here on the right. We have a module called segue, which is the description of the software as a whole. It has a box here on the right, which is giving a platform independent description of the platform by describing that it has events. For instance, left motor velocity. It's an event that allows you to find out what's the velocity of the motor on the left. You have an IMU, and you can find about the angular speed and so on. The software that we are modeling, its objective is to keep the segue upright, right? And it has an important safety property that if it can't do it, if it tips beyond a certain angle, then it stops the motor to avoid any kind of a problem to either property or to people around. And so the software is very simple. Well, I don't want to go on the record saying it's simple. The person that actually wrote the model may not like that I say that. So, but it has a single controller. The controller has a behavior given by a single machine here called balances STM, and then it uses 3 operations which are different forms of PID. But the one that is a completely sequential model. That is the model that's actually implemented. We can transform that model and say, let's have now a distributed implementation of this segue. And in this distributed implementation, what changes is that I have here the main machine, and it's now synchronizing or collaborating with 3 other machines that are implementing in parallel the PIDs. And I can then say, okay, I'm actually going to extract one of the PIDs and make it into a separate controller. And once I've done that, I have said, okay, I now can establish that this separate controller, it is cyclic and it is memoryless. To do that, I can do 2 things. If it's defined by an operation, by the very nature of what an operation is, we can syntactically check whether it is cyclic and whether it's memoryless. But if we have it as a controller, to describe that it's cyclic, basically we need to say that a trace is refined, a process called cycle that receives all the inputs, produces all the outputs, and recurses. So this process is not giving any restrictions on values, it's only on control flow. If every trace of my components refines that, I know that it's cyclic. To make sure that it's memoryless, I can create a restriction on information flow. That is something that Jim is working with us to identify a technique that is related to information flow, to security work that has been done in the context of the process algebra. But here's the specification of what it means for it, or what we mean for it to be memoryless. Basically, we have a notion of what it means for traces to be cycle complete. they are cycle complete with they finish with the sequence of all outputs. So I'm talking about cyclic systems. If traces have all the inputs and all the outputs, and they finish with all the outputs, they are giving the behavior all the way to the end of a cycle. So we consider two traces, T1 and T3. And if T1 and T3, there are both traces of the system, T1 can be extended with T2, right? The end of the cycle can be extended with T2, then T3 should be able to be extended with that T2 as well. So that basically means if at any point I finish the cycle and I can then behave in a particular way, then that can be done in whatever happened before, either T1 or T3. So that is the notion of memorylessness that we are using to ensure that we can then have a chance that that neural network will be an appropriate implementation of that component. So in our case, our Angle PID is cyclic and memoryless, and we have replaced it with a neural network. To define such a component, we give its input size, its output size, and then the parameters of the neural network. We need to give the structure of the neural network, the layer structure, the weights, the biases, the activation function. So what work have we done? We've given a RoboChart module. Now with the extension we've done, it can be composed of state machines or of ANN components. For the ANN components, we have defined a meta model. We have defined well-formedness conditions. And that means that now we have, when we have a model that satisfies these conditions, that's valid in that sense, we can get to a data-rich process algebraic semantics. That data-rich process algebraic semantics can cater both for the ANN components and the state machines to give an overall account of the software as a whole, used in a language called Circus, which is a combination of CSP, of this process algebra that I mentioned, but with a rich data language as well, using another modeling language called Z. With that rich process algebraic semantics, we then enable the work of verification using a variety of tools and notations. In particular, we're interested here in the unifying theories of programming, where, as I said, we're using Isabelle, a combination of Isabelle and Marabou. But as I mentioned, we could use JCSP, we could use FDI as well, the model checker, but that required discretization. It again was an effort that we made just for validation of our work. So here's the meta model. I don't believe this community is particularly interested in meta models. I'll just make a point to say it was a very simple extension. We have notions of controllers and operations. Controllers can now be defined in the standard way using state machines, but it can now be used as ANN. The same thing for an operation. An operation can now be defined by an ANN. And the definition of an ANN, what it really has is the ANN parameters. The parameters will include the input size, the output size. This structure can be given explicitly, but it can also be given by a file, where these files are automatically generated when you train a neural network. These files automatically generated describing that structure that will give the size and the layer structure and so on. So there are well-formedness conditions, basically to ensure that you are connecting that neural network to the system as a whole in the appropriate way. It's well typed, it's well scoped, but for example, if you have that in size and out size, they must be greater than 0, so it must have an input and an output. And moreover, the layer structure, the weights and the biases, they are all no-empty of the same size. If they are not null, because if they are null, it's because there is a file name, and that's where the description is going to be. So you have that kind of a restriction. And what I really want to tell you about today is about the semantics. So the really good news is that a process algebra is a language that was created to describe networks. And a neural network, the clue is in the name, of course it is a network. Okay, so the definition of a process algebraic semantics for a neural network is extremely pleasing, mathematically pleasing, extremely simple. It's very well suited notation to describe the behavior of a neural network. So a neural network, perhaps you all know, it will have a number of inputs, provide a number of outputs. It has a number of layers, and in each layer you have a number of nodes, and these nodes communicate with each other, provide communication from one layer to the next using a particular structure. So to capture this using a process algebra was simple because the process algebra, in particular CSP that we have used, systems and components are defined by processes. These processes, they communicate via atomic and instantaneous events. And the process, what it does is to define the patterns of interaction between these components and establish the events that are possible and the events that are required. But events can represent communication of values, can represent interactions, or where you have a passage of data. For model checking, real values are a real challenge, but we don't need to use model checking just because we're using a process algebra, although it's a very popular way of carrying out verification. And moreover, in the case of CSP, we have the possibility of model time properties. We are actually, we now work with neural networks who use CSP, but the RoboChart also has a talk CSP, a time semantics as well. So in future work, we will be dealing with the effect of the on time of the neural networks. So here's this structure. I don't have time to describe to you the details of the CSP notation, but here's this structure of our semantics, and that will show to you how direct that semantics is. So this outer box here is representing the component, which is the neural network, and that uses one event called layer s, events of the shape layer s.l.n.v, and these events represented communication of a value v from the nth node of the layer L. And layer s.0 events, so considering the layer 0, they are inputs. Layer s.n, where n is the output size, that considers the outputs of the neural network. The other ones are used to represent those internal communications that are here. So what's the structure of the process? The process is defined by the parallel composition of a process called hidden layers that models all the layers, with another one that called output layer that models that last layer that's providing the outputs. The structure of this process is very similar. So, hidden layer is defined by the parallel composition of several layers. These layers, they are talking to each other using events layer as I and layer as I minus 1. So each layer talks to the layer before and to the layer afterwards. And the hidden layer is composed by processes that represent the nodes. So each node, in itself, it has its internal structure, but the structure of the processes matches one-to-one the structure of the neural network. And that's extremely pleasing. It's really nice result to have. In a node, we have processes to represent the inputting of the values from the layer before. They are all using getting those inputs and passing it on to another process called the collator. They use these events, no doubt L and IV, and basically they are recording the ith node for that which it got, and the collator, what it's doing is applying the bias, applying the weights, and carrying out the capturing the semantics of the activation function. So it's a really interesting, very simple structure that it is difficult to challenge and to think there may be a problem there. But with the RoboChart with ANN, we can encode it in JCSP. So JCSP basically providing Java constructs of JCSP. That avoids the discretization that we had to do some very preliminary validation of the semantics. It allows us to do simulation by analysis, simulation and analysis by assertion-based reasoning using JML, for example. So we use doubles to represent the real numbers. We created a class called JCSP ANN that will allow you to encode the semantics of any ANN that you write in RoboChart. And we use JML annotations to validate the model, but also compared it to the C++ and the Python implementation and that with the assumption that the JCSP is a faithful encoding of our semantics, that is a fantastic validation for the work. For verification, what we have is now we have a circuit semantics, both of the RoboChart controller, of the module involving the RoboChart traditional controller, and the module involving the ANN. And now what we have is we can use the semantics of CSP and UTP laws to obtain a UTP account. It's called a reactive contract that uses application-specific events. In another option, in another point, we have the version with the ANN, where we have carried out some sequentialization. That highly parallel model is very pleasing, mathematically very interesting. And what we've done is then to say, okay, if I now want to do some verification, it will be easier if I can eliminate all that parallelism. And we have established that that can be sequentialized to simplify theorem prover at the later stage. And from that, again, using semantics of CSP and UTP laws, we obtain another account in the UTP, now provided, now described using a trace-based specification of the problem. And with those, we then can compare them using the conf relation, and from those we have generated verification conditions that can be proved using Isabel. And if you are happy to bound the set of values that you are going to deal with, we also get reachability conditions that can be used to combine use of Isabel UTP and Marabou. So, sequentialization. I will not tell you very much about this. I've already explained. It's a direct view of the network and a common parallelization strategy to implement the code of your neural network. It's a sequential model for one iteration. For one iteration, it's simpler to reason in the UTP to use a sequential model, and that we have established that it is equivalent. But what is this UTP that I've been telling you about? Basically, as I said, predicative relational semantics that can cope with a multitude of paradigms. It's a very simple but very powerful idea. We have theories in the UTP that can deal with time, with object orientation, with hybrid models. It is really very, very powerful mathematical framework. And the powerful idea is that we have predicates over variables and their dashed counterparts to represent the fact that we have initial values and then subsequent observations of the behavior of a system. So a very trivial example, I can say x dash is equal x plus 1 is a model, with a relational model of a assignment, but I have extra observational variables to capture time, stability, time, termination, concurrency, all sorts of things, and also a notion of refinement. For the particular work that we are doing here, we are using the reactive contracts theory that allows us to define preconditions of your mechanisms, post-conditions of your mechanisms, but also periconditions, which describe behavior when the system is stable, pausing for, waiting for interaction that has not terminated yet. So, here's an example of the general pattern of contracts that will be obtained that can be used to give semantics of a neural network. So there has three parts. So the contract, it's called in red there, general ANN contract. It has a precondition true. That means to say every neural network, we assume, except for lack of resource, that always terminates successfully. And then it has a pericondition, which has two parts here, and a post-condition. These are described using tr dash and tr, or variable tt, which describes what are the interactions. Tr is all the interactions that happened before the mechanism started. Tr dash says what are the additional, extends tt, tr, but saying these are the additional interactions that we have. And so we have here the three possibilities. We talk about a trace called input that comes from this difference between tr dash minus tr. So it comes from the contribution to the events that the mechanism has done, which are all from events layer as dot zero. Those are the inputs to your neural network. And what we say is if this number of inputs is less than the number of inputs required by the neural network, then we use this epsilon constructor to say, well, that means that the trace we observed so far is just the inputs. and the next input, which is less than res 0 size of input plus 1, is not refused. Or I've got all the inputs, but there is a layer, and a node in that layer where I have here this trace specification given by layer output, where all those events have been provided, but the last one, which is the output of the node N of that layer, is not rejected. Finally, I have the situation where the input is size, but it's the post condition, the system has finished, and therefore all the outputs are provided. This is provided by this phi predicate there. So that's the specification. And this, the theorem that we have is that the semantics of those hidden layers process and the output layer can be expressed using that general pattern. That's very important. We also have a pattern for the cyclic memoryless controllers, and I'll give you an example as easier to understand. The cyclic memoryless controller also has precondition true, and that here has its paired and post condition together. For our example, the inputs are Kerr new error and Kerr diff, and the output is Kerr angle. So the pattern says I have the relationship between the input and output variables as defined in the RoboChart original model. And then I have the paired condition saying either I haven't got any outputs and it's not refused, or I have got one of the outputs and the next one is not refused, or I have got all the inputs and therefore the output's not refused, or I have finished and therefore my trace contains all the events. So that's the structure that we can deal with. And now we want to ask, what's the relation of what's the conformance? When can I say that a neural network Q is conformant to a traditional controller P? Basically, what I really wanted, if I could, is to have refinement, which is this symbol here. But I can't. So what I say, well, Q is a refinement of P is slightly modified. And what's the slight modification? The slight modification is that we say the traces and the refusers, they are replaced with these two, S and alpha P minus Y. And what are they? They are approximations. They are existentially quantified here, introduced, and they are approximations of the original values. And these functions, outsec approx and outset approx, they are outputting, they are approximating the outputs. And so we're basically saying, if I can relax my specification and allow the trace to have a different value that is within the boundaries of the epsilon, that's what outsec is saying. My refusers to have events that are similar but values that are in the bound of epsilon, that's what they're saying, then conformance holds. That's the novel notion of conformance that we are putting forward. And then we have theorems that are important. First of all, of composition. If I have a refinement and then a conformance, then I have conformance to the original specification. That justifies the approach that I said, where you start from a system, you use, like we've done with the segue, we use the standard refinement to transform it, and at the last moment, you then say, no, it's a neural network, there is an issue of approximation. So I can compose refinement and conformance. Moreover, I have to worry about the effect on the rest of the system. And there are two possibilities with the context where the neural networks put on, either is completely oblivious to any small changes by epsilon, or it does not make the problems worse. So if it does not make problems worse, we say it's stable. So if P is conformant to Q, according to an epsilon, then the whole system, including the C, is also conformant to Q according to that epsilon. The same thing for refinement. Now, if C is epsilon tolerant, you change it a little bit and it doesn't note, then if I have P conformance to Q, I have the whole system is refined when I actually change one for the other. Okay, so those notions of stability, imprecision stability, or imprecision tolerance, they can be defined in the same way that we defined conformance. So we say that P is absolutely stable if P conforms to itself when there is a certain perturbation. And now the approximation is in the inputs, not the outputs. So what I'm saying, if I perturbate the inputs of P, and it doesn't change its behavior, it's still conformant, then we have stability. It hasn't made things, it's not a component that makes things worse. The other one is that it's tolerant. It's tolerant if, when I compare it to itself after I've made some changes to the inputs, we still have a refinement. So in that case, you can change, you can have your imprecision, and that context is not going to be affected by it at all. And again, here I'm talking about inputs approximation. So with these notions, I now want to prove conformance. How do I do that? To prove conformance, I can look at, well, I have those patterns. Remember, I have those patterns. The patterns are pre, post, and peri conditions. And basically what's been very pleasing is that if I have Q and P that are instances of our patterns, Q is conformant to P, provided the conformance distributes to the peri condition. This is the definition of conformance for Q2 and P2 that I'm using to refer to the peri condition, and to the post condition. That's basically what we're saying. So that is very, very pleasing mathematically as well. And even more, that's where we can bring in Marabou into the story, is when we say, I have another theorem that says what I actually want to prove is that the system, once all the hidden events of the neural network are hidden, all the communications of the hidden layers of the neural network are hidden, and the inputs and outputs are the actual inputs and outputs of the system, is that conformant to my P, to my original P? And we have found a reachability condition that describes that when this happens. And this reachability condition says, well, there is no as values of inputs and outputs as described by the original model, such that the corresponding output of the neural network is outside of that bubble where the only change that we have to the values is epsilon. So that is a theorem that says, you want to prove conformance, you can describe it as a reachability condition. And with that, then we can use Marabou. If we if we accept the fact that value is a bounded set, then we can use intervals to represent that space. And with those representations, then use a tool like Marabou, which is the standard tool for neural networks. So to conclude, summary, what are the things that I'd like you to remember? This is, there's a lot more information in our papers. What we have is an integrated approach to reason about ANN using a variety of techniques. We have support for analysis by assertion, for simulation, for proof. You could try model checking, perhaps the powerful servers of AWS, but let's see. Simulation, Java, and conventional proof assisted by Isabel UTP, and consistency established by a common front end, which is the Isabel UTP framework that we put there. Future work, timed models, the generation of the simulation models, additional case studies, and also to deal with neural networks when they are tackling the very difficult problem of perception, where then what's been very pleasing here is that we have a traditional controller as the specification for our neural network. What happens when we don't have that? Our framework gives you some indication of what you do if you can characterize your property, but there is more work needed. Thank you very much for your time and attention. Thank you.
Thank you. I think we have one question in the online.
Just someone from the Q&A just wanted you to clarify what is Drake.
What is Drake? Drake is a simulator for robotics, and it has a physics engine. It's there because it's one of the many simulators that we are providing support for. One difficulty that we have in translating the models that we have in RoboStar, nothing to do with the neural networks, is that we have mathematical models that describe the behavior of the systems. when we put it in a simulation and it has a black box physics engine that is simulating the environment and the physical properties of the platform, there can be a discrepancy. We won't, in some cases, we won't even know because they're black boxes. Drake is one of the best of them. It's not an entire black box, and that's why we're working with Drake. Okay.
Any questions from the audience?
Please.
What's Isabel UTP? Is this different to, there's Isabel Hall and Isabel ZFC? Is this yet another one?
Okay, so Isabel UTP is a mechanization of the unifying theories of programming using Isabel Hall.
Oh, so it's on top of Isabel.
It's on top of Isabel. It's not a different tool. No, it's not a different tool. Okay, it's a very large collection of theories that mechanize the notion of what is a unifying theory of programming theory, and that's why it is being used by us. Okay.
Do you use things from the Isabel Hall ecosystem, like stuff from the archive of formal proofs, or you just written everything yourself?
We are contributing to the AFP.
Oh, you are?
You are. Yeah. Are you an Isabel person?
No, I just.
Yeah, we are contributing to the AFP. We do use the libraries of real numbers, for example. But we contributed with a theory of lenses, for example. All our work over the years. There are actually, I have to say, 2 versions of Isabel UTP, and all our work over the years have been put in the AFP.
You say you used the real number. You mentioned doubles earlier, and I thought, well, how are you going to prove anything?
Those is for JCSP. That is for using Java.
That's when you're using Java.
That was for
Java.
Yeah, that was for Java. Yes, that is. So we wrote the semantics, and then while we write this process algebra semantics, we always ask, have we made a mistake in writing this mathematical model? So discretized, used FDR. FDR can't go very far. And also just discretized model. So then the idea was to encode it in Java using the JCSP library, and then we could have doubles, and then we could run simulations and compare and give us more confidence in the semantics, to validate the semantics. That's what the work was doing. Thanks.
Any other questions? You mentioned about the timed models. So from your perspective, what do you think would be really the challenge to handle that, or it's just the next step?
I don't know. I'm very keen for us to really wrap this up and start talking about time. RoboChart has an untimed model where we basically do not capture any of the deadlines or any of the time budgets and so on. But it also has a timed model, which is written with a variation of CSP called TOC-CSP. So TOC-CSP has model checking support using FDR. And with TOC-CSP, we are able to say this operation needs to happen with at most some amount of time, or we expect an input from the environment in at most certain amount of time, and so on. So for the nature of, just for the difficulty of the problem, we started with the untimed model. But the questions that we will need to answer when we come to deal with the timed model is, what are the time properties of your neural network? How long do you expect? What does it need a budget? If it's a very small network, you could say, well, we call it's instantaneous, it's running parallel, fine. But if not, what's the impact on the timing, on the capabilities of your of the performance of your robot? And that's what we will need to think about, how we want roboticists to worry about modeling that. Yeah, and that is at an abstract level. When we come to simulation, we will need to solve that problem. How do we schedule the neural network inside a cyclic simulation? So that's the kind of thing that we will need to think about. Okay, I expect that that's when we will need to really deal with parallel simulations. The community is not very keen on that. We're even a bit, how do you write what is the structure that you use when you are writing parallel simulations? What parallel simulations? We don't do it, but we need to tackle that. Okay.